Alright, I'm going to do these notes just a little slightly different here. So this is it. This is the end of 3.7, which is differentials, right? And so we didn't get to 3 problems yet. So let me zoom in. I'll kind of zoom in, zoom out here. So where we're at here, if you guys remember, we were at approximate, right? We were approximating. That's what we were. We were approximating the square root of 1.1. And then the next one, we approximated the square root of 5. And we also noticed that, you know, once you get a little bit away, it's not as close. That's kind of where we got to here. So let's jam. Let's jam with the rest of this here. So we are on example 4. Example 4 says, can you approximate? There you go. Approximate cosine of 62 degrees. That is it. And then if you want to write something more with it, how about without a calculator? Ha ha ha, got you now. Okay, how's this going to work? Okay, the one thing that we got to make sure that maybe put a little side asterisk here. So we are going to use radian measurement, because once you look at slope and once you're looking at tangent lines, you want real numbers to be there, not degree values. So before we do anything else, let's go with and let's change this into radian measurement first. So you know, since I'm going to use 60 degrees, I don't want to change 62 degrees into radian measurement. And so let's do this here. You guys should know this here from trig class here. So 60 degrees as far as radian measurement is concerned. All right, so I'm going to just kind of plug this way. The degree sign goes away, the zeros go away. We're left with 6 pi over 18, and eventually, how about a pi over 3? Cool. Okay, we are going to add in, right, technically, we're going to add in 2 degrees. So we should do that. So 2 degrees added in would be 0. The degree sign goes away, and we're left with what, 2 pi over 180, and then we can reduce those by 2, and we're left with pi over 90. Okay, so there it is. That's 60 degrees. That's 2 degrees. You know, we probably should do that. Yeah, we should eventually we should, because we're going to plug in, technically we're going to find the function at 62 degrees. So you can convert this using this way if you like. We're kind of going to set up everything we need. You want to do it that way, that's fine. Okay. The other way to do it, since you know what 60 and 2 is, you can just do this here. You can say, hey, look, I'm going to add 60 degrees equivalent plus the 2 degree equivalent. So the only thing I got to do here, I got to multiply this side by 30, this side by 30. So it looks like 30 pi over 90 plus pi over 90 makes 31 pi over 90. Done. Okay, there it is. There's my equivalent for 62 degrees. Okay, now let's start with the problem itself. Let's zoom out. Let's see where we're at. Okay, so what function are we talking about? Technically, we're talking about the cosine function. That's what we're talking about. Okay, and what we're going to do is we're going to take the derivative of cosine, which will just be negative sine of x. Voila. And what we really want is we want the derivative of negative sine at pi over 3. So negative sine at pi over 3 gets me a negative root 3 over 2. Voila. Gotcha. Next is the approximation. Here it is. We are going to approximate this function at 31 pi over 90. And approximation is going to be these little guys right here. Approximation. Alright, and the formula for it, as we have learned, is the derivative. Whoa. Come on, go away. I don't need you here. There it is, okay. The derivative is pi over 3 multiplied by the little extra that we're adding on to it, plus the function at the spot that we know already. Dunk, dunk, dunk. So approximation is, this would be negative root 3 over 2. This would be, we already have it, it's just pi over 90. Plus 1/2. That's what we have there. Moving on down. Putting it all together here, let's see, that'll be negative pi root 3 over 180. And the 1/2 really turns into 90 over 180. And so simplest form is negative pi root 3 plus 90 over 180. Alright, and so if I said I wanted the exact value, that would be the exact value. If I wanted on the test, for instance, if I said approximate that, maybe like what, to the nearest thousandth, I guess. How about that? To the nearest thousandth. It would be 0. In fact, no, let me go just a little bit more. Let me go a little further. So 4, 6, punching this in from my calculator, 9, looks like 7, 7 is what I got. And then I'm going to take my calculator real quick here. Take your calculator and just punch in cosine of actually 62 degrees. I want to know what the calculator says. It is the answer, and let's see if we are off. So the calculator answer is 0.469716. Hey, that is pretty close. Dunk, 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 dunk. So we're off at this point right here. So this is right there. So we're off really by 0.003 approximately with that. All right. Okay, so now that is called, if we calculate actually how much we're off by, right? That's what we want to do next. So let's keep on going. And so what we say is this right here. Let me give you a quick little definition. So this is called error, propagation. All right. And so it's kind of like the study of air. How much air do we have? Or how much computated air do we have? So this is going to be what? Example or exercise number 5. Let's go with it. Exercise number 5. It says this. So the radius of a sphere is measured to be 50 inches. That's great. Now is it 50.00000 inches? It depends on the instrument we use, right? So so here it is. Now this is based upon the instrument. With a possible measurement error of plus or minus 0.02 inches. Voila. Okay, so what's up with that? So if the radius is off, anything I'm going to calculate with that radius is going to be off as well. So let's do this here. Estimate the possible error in the computed volume of the sphere. Okay. So we're going to compute. So we know if we have a r radius that is off by that much. Now the question is, how much is the volume would be off by if that's the case? So let's jam with it here. So if you guys remember, what is the volume formula for a sphere? So volume formula for a sphere is 4/3, right? Pi r cubed. There it is. And so what we're going to do, we are going to take a derivative. Let's go with it here. So we're going to say this. In fact, we're going to say, let's see, dv dr, right? Because we're taking the derivative with respect to the radius here. So with respect to the radius, that means that 3 is going to go out in front, the 4/3 out in front. 3 comes in as a multiplier. We have pi r squared. And eventually we got ourselves, what, 4 pi r squared as dv dr. Okay, and we'll kind of think about this here. What does dr mean, right? And what does dv mean? We can change these if we're going to start approximating things, right? And so off to the side, is that true? So this is approximated by that, right? And this is approximated by that, right? In fact, hold on, that's not an approximation, right? If r is kind of like our x coordinate, so those guys are exactly the same. So let's do this here. Let's see if this makes sense. If I do this, I'm going to go dv is equal to, right, I can just multiply both sides by dr. And then I say to myself, you know, that's true, it's very kind and dandy, but we have this right here now. So the difference in the r can be approximated, right, by dv and this little formula right here. Or even better yet, right, can you technically say this here? Approximated, let me erase that, approximated by 4 pi r squared dr, right, the difference there. So let's go with it, let's plug in some numbers, let's see what we got. So 3.14 r squared is, or actually no, let's put, because we're trying to be precise here, let's put pi in here just to make sure that's the exact thing that we want. Alright, we're going to put 50 in for our value, and we're going to put in plus or minus 0.02. Punch that in the calculator, see what you guys get. Alright, and you should have got something look like this here, plus or minus 628.32. There it is. So then what, let me do this here. Let me calculate. Let's calculate how much we could be off by, right? This, pi r cubed. If we plug in the 50 in here, if it was exactly perfectly measured, right? We would have got 10,471.96 repeating, so 97. Right, so that means this is the calculated measurement of the volume, and then it's a plus or minus that to the volume, which kind of makes you really consider significant figures, right? Significant digits. Also makes you want to consider the stuff that you test with, right? How close is that? We were off by, look at this, we were off by a minuscule amount, right there. Look at that. We were off by 0.02 inches. That's how off we were. Like, can you actually measure that with the human eye? I don't think so. And then you have this much air in the volume itself. You can be off by 600 units, in this case inches, from the volume itself. So anyways, free to think about there. Okay, let's keep on going. And so a few things we got to think about is something called relative air. Let me give you the formula. It's Q is going to be just an arbitrary variable. So delta Q over Q, which would be like approximately, and again, didn't want to use R, didn't want to use anything else, so just Q, just a random variable. That's what that is. And then we have percent air, which we'll kind of see in just a little bit here. So those two ideas here. So relative air, percent air. And let's keep on going. See, that's 5, so this is 6, 6. So question is this. Calculate. Let's use the same numbers that we had before, so I have to think of new numbers here. So how about this? calculate the relative error and percentage error in R and V. That's it. So give me those. Calculate the relative error and then also calculate the percentage error in this. So let's talk about, I'll just put RE, relative error. So we need relative error for R, then we also need relative error for V. Then we want, let's see if I can put it underneath. Let's see if I can put it on the side afterwards here. Okay, so let's go with it here. So what's the relative error for R? And if that's the case, we're going to say this. We're going to say the relative error for R was the derivative, right? The derivative of R over R. That's what we have. In this case, it was plus or minus 0.02 inches, right? Divided by 50. And plug that in, and you get yourself equal sign plus or minus 0.0004. Right? Notice the inches are going to fall off, right? So this is just relative error. So this is almost like a ratio of error for that particular piece. Let's do this one here. So then relative error for the volume was going to be the dV over the V itself. So in this case, it's going to be, you know what we can do? Instead of putting in numbers, how about we take the derivative and then the formula itself is this right here, right? So let's see what we come up with here. So what happens here is that the 4's are gone because the 4's are canceling each other. The 3 goes on top because it's the denominator of a denominator. That goes on top. The pi's cancel. We're left with 1 R on the bottom and with a dr here. So really, look at that. Of course, volume and radius are connected, aren't they? So really what this says is the error in just the sheer ratio of the volume itself is going to be 3 times whatever we got for the error of the radius. In this case, it'll be plus or minus 0.0012. Okay, so really, what are we trying to get to? We're trying to get to eventually percentile error, or percentage error. That's what we're trying to get to. Okay, so the percentage error for R is, it's going to be plus or minus 0.04%, and percentage error for the volume is going to be plus or minus 0.112%. So again, if you think about it, eventually when you calculate the error itself, it was less than 1%. Right, because you kind of think about this here. So you have 10,000, right? It was 10,000 units. 600 was the error. So, okay, overall, maybe not as bad. All right. So, anyways, so hopefully this completes for you the lecture for 3.7, and hopefully now we can finish up the techniques for differentiation.